Hey everyone, so this is your Kinetics Part 2 notes. We will be kind of talking about a little bit of what we did last class in Kinetics Part 1, but also exploring some new equations. So just as a review, last class we talked about differential rate law equations, and we had zero order, first order, second order, and then some more complex ones that we won't really talk about. So we have our instant rate equations just being k times some concentration to one of our exponents. So our exponent is basically telling us, is it zero order, first order, or second order? These terms apply to the exponents in the rate equation, but remember that we are figuring those exponents out based on data that was found experimentally. It has nothing to do with the coefficients that are in the reaction. And we always write these equations in terms of the loss of the reactants or in terms of gain of products. So that negative sign may or may not be included on those equations that we used last time. Also, we don't usually even use the term instant. When we use the word rate, we just assume that it happens at an instant. So here's some new stuff. It says, what if I wanted to calculate the concentration of a chemical after a given amount of time instead of at an instant? So instant rate equations are great when we're calculating the speed or the rate of a chemical if we know its concentration at a point, but they don't allow us to calculate what happens over a given amount of time. Again, we're going to use calculus a little bit, but we basically already have these equations. So the new equations that you're getting today are called the integrated rate law equations. So it's really similar to what we did last time. You're just figuring out which type of equation to use. Here are the three that you're going to see. So we have zero order, first order, and second order reactions. Depending on what order of the reaction, you will use whichever equation that it matches with. This time we do kind of care about that negative. It ends up canceling out at the end, but it will change some of your math. So go ahead and keep that negative on the K. When using these integrated rate law equations, concentration or pressure in any unit can be used as long as the units are the same on both sides of the equation. These are all written in the y equals mx plus b format. So this time we are going to look at graphs, and that's going to help tell us what type of reaction it is or what rate order that it is. So if I have a graph that on the y-axis it's concentration and on the x-axis it's time, and that slope is just a straight line, then that's a zero order reaction. If my y-axis says Ln of the concentration, which is natural log of the concentration, and my x-axis is time, and it's making a straight line, it's first order. If my y-axis is 1 over the concentration, and it's still a straight line, then it's second order. So on all of these, the order of the reaction is really just based on what that y-axis is. So again, if I have concentration over here and time over here, and it's making a straight line, that tells us that it is a zero order reaction. Let's say I have concentration and I have time, but my slope looks like that. That's not a straight line, so it was not zero order in this instance. It has to be a straight line. So really you're looking at the y-axis and you're looking at what that graph is doing. Here's an example of that. So in these three examples, they're all straight lines. The only difference is how the y-axis is labeled. So I have concentration, natural log of concentration, and then 1 over the concentration. Here's a bunch of data. We're going to come back to this in a second. And let's look at this example. So this says nitrogen dioxide gas is used to bleach flour, catalyze organic reactions. It's used as rocket fuel and is very toxic to humans. It decomposes into nitrogen monoxide gas and elemental oxygen gas. The following data was obtained during an experiment decomposing nitrogen dioxide. So we have a data table we'll come back to. Hopefully it'll let me go backwards, we will see. First, we have this reaction. So I will always give you that reaction on the test. And the first thing that it wants me to do is figure out if it's zero order, first order, or second order. So let's see if it'll let me go backwards. So this is where I can look at this data. This is the data for this problem. So if I look at that top right chart, the dots are not making a straight line, so I don't care about it. The one right under that, same thing. My dots are not making a straight line. The only one that is making a straight line is the bottom left. If you look at the title, it says the natural log of concentration versus time. The y-axis is really hard to see, but it also says natural log of the concentration. So, according to my rules and my equations, if it's natural log on the y-axis, this is a first order reaction. All right, so we're gonna answer these questions one at a time. It says, write the integrated rate law equation for this reaction. Okay, well, we know that it's first order. So for first order, we have natural log of the concentration, this is of NO2 because that's our reactant, equals negative K times time plus natural log of the concentration. I think this is initial, this is after a period of time. Okay, so I kind of filled this part in for you just now. So it looks like that. Okay, so number one is done. Number two, determine the rate constant. So this time I am solving for K. I'm going to change colors. Maybe. Oh. Okay, so that was number one. This time I'm solving for K. When I'm solving for K, I need some data to plug into my equation. So it says, now that we have a time-based equation, we can use the initial concentration and any other concentration and the time that has progressed between them. So easiest thing to do, use your first two data points. So I'm talking about the data that was given in the chart a few slides earlier. So let me just show you where that came from, and we'll come back to this. Maybe. There it is. Okay, so this data table. So I have natural log, and I'm going to leave this first one blank for a second. Negative K times some period of time plus log of my initial concentration. So my initial concentration is 0.368, losing room. Okay. So my second data point, my second concentration after a period of time was 0.135. If you look at the time between those two intervals, it's 100 seconds. So time always needs to be in seconds. Go forward. Okay. Whenever I am solving this, I'm going to plug in those natural logs first. So there's a button on your calculator that says LN. So click the LN, type in 0.135, and write out what that is. Let me grab a calculator, and I will do this with you. Give me 1 second. I'm going to do that for the natural log of 0.135. I'm also going to do that for the natural log of 0.368. So these, I feel like it's really important to do it one step at a time. Don't get too far ahead of yourself in the calculator. So I got -2. When I did natural log of 0.368, I got -0.99. So here's what I have so far. Next thing I would do is add 0.99 to that other side. So -2 plus 0.99 is a -1.01. That's equal to negative k times 100. I'm trying to get k by itself, so now I'm going to divide by 100. So I got negative 0.01 equals negative k. Those k's cancel out, so my rate constant is 0.01. Okay. Number 3. Switch colors again. Let's do green. Okay, number 3 says, what would the amount of NO2 be remaining after 6.2 minutes of the reaction progressing? Use appropriate units. So we cannot have minutes in this equation, so the first thing I'm going to do is convert that into seconds. And I'm going to use my same equation. So I have ln. I don't know what this concentration is going to be. That's what it's asking for. K we just found is negative, or it was a 0.01. My time, they gave us 372 plus natural log of 0.368, which we already found up here. So I'll just plug that in so I don't have to put it in my calculator again. Okay, so I just need to solve that right side. So I'm going to do negative 0.01 times 372. So negative 3.72 minus 0.99. That is equal to negative 4.71. So now, if I'm solving for x, I have to do the inverse of natural log. So in your calculator, that function looks like this. So I'm hitting second ln, and I'm gonna say, it's gonna say e, and then it's gonna end up looking like this, I believe. And that will give you your answer, which is 0.0089. And it's molarity, it's concentration. Next question, switch colors to blue. Let's do this color. Okay, number 4. How many seconds to reach that specific concentration? Remember that capital M is molarity, that's telling us concentration. So same equation. This time it's telling me that concentration is 0.00475 equals, K is still the same thing. This time I don't know the time. And that natural log is still 0.99. Just took that from here. Okay, so I'm going to do ln of 0.00475 negative 5.35. Next thing I'm going to do is add 0.99 to that. So negative 4.36 equals negative 0.01 times temperature. If I want temperature by itself, I'm now going to divide by negative 0.01. Let's make sure we're doing all this math right. Perfect. And I also got this in my calculator. It's going to be about 435 seconds. 436 maybe if you round. We're almost done. Okay, now it's asking for the half-life. There's 2 ways to do this. The first way is we can take the initial concentration, that was 0.362, we can cut that in half and then plug it back in to this concentration and solve for time. That takes a little bit. There's an easier way. The easier way is to use integrated rate law equations and equations that have already been produced for half-lives based on what the order of their reaction is. So in your slides, you have this chart. If you look second from the bottom, that light blue row, it says half-life. We know that this is a first order reaction, so we can just use this equation. 693 over K. We know K, because we solved for it already, and it was 0.01. So if I want half-life, all I need to do is divide those. On the test, I will give you this chart, so do not stress about memorizing those because you will have them there for you. So when I divide those, I should get 69.3 seconds. That is my half-life. Okay, this should give you enough information to be able to do those guided practice problems, but please, as always, let me know if you have questions. Bye, guys.